Let's have a look at some gravitational fields questions. The first one here we got is a definition. It says define gravitational potential at a point. You need to know what potential is. You can't really understand what it is without the definition. So it is the work done, or you could say energy required, but work done to bring 1 kilogram or a unit mass from infinity to a point. Now, this is really important. Gravitational potential is always negative, so therefore it's 0 and infinity. So the work done is to bring it in. Next question we've got says we've got some equipotential surfaces at different distances from the center of the moon. It says explain how the surfaces in figure 2 show the gravitational field is not uniform. So the best thing you could do here is look at an equation sheet to find, well, we're talking about gravitational fields, but we've also been given equipotentials. So how does gravitational field relate to equipotentials? Well, we know the relationship between gravitational field strength is equal to the change in potential divided by distance, or what's called the potential gradient. So we've got to look then at the change in potentials and the change in distances and see if it's going to be constant for each one. Now, we don't actually have to look very hard to figure that one out, because we've got constant differences between the gravitational potentials, but the distances change each time. Those distances are not constant. So we'd say something like the potential difference is constant between each line, but the distances are not. And you can even quote, usually a good idea to quote equations in your answer and say something like, I know that G is equal to change in potential divided by change in R. So therefore, this value here is changing, so G not constant. Now in the mark scheme, that top one is absolutely fine for a mark, but that extra detail could come up in a future question, so it's worth knowing. Next, we've got to use this figure to calculate the escape velocity at the surface of the moon. Now, this is a really important derivation you need to know how to do. You won't find it in your equation sheet. We need to know how to derive it. So the idea is for escape velocity, we're going to equate together kinetic energy and gravitational potential energy. So equation for kinetic energy is straightforward. Gravitational potential energy is really sneaky. They don't give it to you. They do say that work done is equal to mass times by change in potential. And then they say, well, actually potential we do give to you is equal to Gm over R. So therefore, if you times that by mass, we've now got that second line we can fill in as Gmm divided by R, and that equals half mv squared. So let's make the equation easier, get rid of our masses of the object, and try and find what V is. We can put the 2 over to this side, and then square root the whole thing. But if we look really carefully, we're not going to be able to find what we're looking for, because we do not have the mass of the moon. We do have R, we do have G because it's a constant, but we need to find the mass of the moon first. So that's why it's 4 marks in this question. We've got to go back and try and find that out. Now let's find another equation from the information we're given in figure 2. That's our clue, and it tells us the radius. So we have to use another equation to find the mass. The one we're going to use is potential equals Gm over R, because that's got mass in here, and we're trying to find the mass of the moon. We do know the potential, so we just need to choose basically any 2 points, so any distance and any potential from this figure down here. So I'm going to use the top one. So I've got, and I'm going to rearrange for M. So M equals RB over G. I know technically it's negative, but it doesn't matter here. And we're just trying to find the mass. So just the numbers we're looking for. So I'm going to use the top values. So distance and gravitational potential here. So I've got R is 3.06. Be careful on the label. It says that's times 10 to the 6. Potential is 1.60 times 10 to the 6 also. Divided by the gravitational constant, which is 6.67 times 10 to the minus 11. Plug those values all into a calculator. You should find the mass of the moon comes to something like 7.4 times 10 to the power 22, which seems reasonable. It's not as big as the Earth, but still pretty, sorry, it's not as heavy as the Earth, but still pretty heavy. So now we've got that, we can just drop it into our equation for the kinetic energy. So it's 2 marks for getting that far, 1 mark for deriving the equation for kinetic energy, and it's going to be a mark for finishing off. So 2 times by G, which I've written down there, times by our new value for mass, and divided by R. So R, what we're going to use again, this time it's the radius of the moon, so be careful, we're not going to use one of the radiuses from the previous bit in the question. If you plug those numbers in, you should come up with an escape velocity of, it's about 2.4 times 10 to the power 3, or 2,400 meters per second. Let's have a look at this question about electric fields. Now, it starts off with a very, very odd question. It's very little information given here. There's no diagram given in question 3. It says an isolated solid conducting sphere is initially uncharged. Electrons are then transferred to the sphere. State and explain the location, so where are they, of these electrons. Okay, so a little bit of an odd question, but if you can imagine it, we've got a sphere and it doesn't have charge originally, and we put a bunch of electrons on it. What are they going to do? Okay, so there's a couple of things you can mention in the mark scheme. The easiest one to talk about is, well, how the electrons arrange themselves on the sphere. Okay, so I think the easiest bit to say is the electrons would be spaced evenly. And the reason they get spaced evenly apart is because they repel each other, basically, or they exert a repulsive force. Okay, so as we repel each other, and it's an explain question, so let's go into detail due to having the same charge. Okay, you can also talk about they go on the outside of the sphere as well. That's good enough for our 2 marks. Let's move on to the next question, which is a lot more typical sort of question. We've got a graph shows how electric potential varies with distance from a sphere. It tells us the radius of the sphere is 0.1, which we could figure out because that's this value down here. So what are they asking us about this then? They're telling us, they give us an equation, which is quite handy, tell us how field strength varies. Field strength is determined by the potential gradient, and it says calculate the magnitude of the electric field strength at a distance of 0.3 from the center of the sphere. Now, to do this one, this is essentially known as the potential gradient. So how do you find the gradient of a curved line? We are going to have to get a ruler out and draw a tangent. So it's at 0.3, so let's put a dot there, and we're going to draw a tangent. Now, top tip with drawing tangents, take your time because it's usually worth at least a couple of marks if you do it properly. Make sure it's the same on both sides, okay? So it should be equal on both sides of the point, so touching the line for about the same length, and do the triangle as big as you can. It'd be a really, really good idea. So therefore we're finding the gradient of the tangent at this point. And you've got to do as big a triangle as possible. However, here I'm going to go with my y-axis. It goes from 0 to negative 1.2. And my distance goes from 0 to, let's work that quite nicely, 0.59. So if I plug those numbers in, mine works out to be 2.033. And because it's everything, here's the 2 sig fig, so I'm going to go with 2.0. And we do get marked for units here. So the 2 units for electric field strength, the most easy one here is because you've got volts on this axis, meters on that axis, you can say volts per meter. Okay, in the same paper, we got another question about fields. This time we're talking about gravitational fields. It gives us this slightly confusing looking diagram. It shows that lines in figure 4 show the shape of the gravitational field around 2 stars. Compare, with reference to this, the masses of G and H. So essentially, which one is going to be heavier and how do we know? So if we have a look at the lines we've got coming in, if we count them, I've got 1, 2, 3, 4, 5, 6, 7, 8. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 lines going into G. So that helps us figure out which one's going to be bigger. So the idea is G is, sorry, not bigger. G is heavier, has a higher mass. And how do we know? So we've got to be really specific with our language here. So we've got to talk about either gravitational field strength or potential. Okay, we can't just say, oh, it's got more lines going into it. So the reason is it's got a higher gravitational field strength. And how do you know? Well, it's just because it's got more field lines. Okay, next question, we're going to annotate the figure to show the field direction at X and the field direction at Y. Here are 2 points. So generally speaking, it is always a good idea to use pencils with these questions. However, I'm going to go quickly. So the whole point of field lines is to show the direction of basically which way a positive mass would go, or a mass would go. If it's an electric field, it'd be a positive mass, okay? So they show the direction essentially of travel that a mass would move in. So for each one, which way is it going to go? Well, at this instant, this one's going to go sort of towards the center of this planet or this object, and this one is going to go towards the center of this one. It's got to be kind of tangential to the curves, which is a bit of a pain to draw. something like that. It doesn't have to go exactly towards H because it has to go at a tangent of where the line is at, and that's what we need to say for that mark. Let's work out for the next one. The radius of an asteroid tells us the mass, tells us gravitational field strength, and we're trying to find the radius. So the equation we are going to use is gravitational field strength is capital G m over r squared. So therefore, to rearrange it, r equals g m over gravitational field strength, all square rooted. Plug our values in, so 6.67 times 10 to the 11 minus 11 times by our mass, and then divide by g, which it tells us in the question. Square root the whole thing, should get you 1.8 times 10 to the 5 meters. Next over here, we've got to plot a graph of gravitational field strength against distance, and we've got to sketch it. Okay, so we've got to be careful when we're sketching graphs because often Mark Scheme talks about how what points you've got to go through, etc. So it should start because it tells us the gravitational field strength at its surface is 0.4. So we're going to start at the top there, and what the graph's asking you to do, we should know it's a curve. Where it's like how much does it curve by? What's the relationship between G and R? So from this equation here, we should know that G is inversely proportional to the square of R. So what that means is if I double the distance, what's it looking for here? Well, I should know that this is going to go down by a factor of 4. So that's going to be here. And then similar, again, we've got this time 3R is going to be there. So again, do it with a pencil, but I'm doing it quickly. It should have a curve that links together those points. Just like that. Okay, now next is what is represented by the area under the graph between R and 2R. So we're talking about this value here. So anything that's got area under the graph is the X multiplied by the Y-axis. So here we've got G times by R. What does that equal? Well, if we look carefully, we have got an equation in our datasheet that tells us gravitational field strength equals change in potential divided by R. So if I move that R over here, what we then say is that G times by R, or a change in R, is equal to potential. Okay, so potential, not just potential generally, we've got to look at what distances we've actually got. The potential we're talking about is going to be the change in gravitational potential between those 2 points. So change in gravitational potential between R and 2R, basically, whereas it's moved from moving between R and 2R. Okay. Now, actually, the second mark for in this question is to figure out, is it an increase or a decrease? Okay, so it's getting from R, getting further and further away. So the potential is actually increasing. So potential at infinity, V is naught. So anything that's getting closer to that means it's increasing, but it's still negative. So it's getting further that way. So it's going to be an increase to get to that point instead of a change. Okay, let's have a go at a couple of multiple choice questions all about this topic, gravitational field. So start off up here, we've got the moon orbits the Earth in 27 days. What's the angular speed of the moon's orbit? So angular speed is equal to 2 pi divided by the time period. So all we need to do is to put the time period into seconds, basically. So time period tells us 27 days times by 24 times by 60 squared. So we need to stick that into our calculator. And we should get 2.7 times 10 to the power of minus 6 radians per second. Next one might take us a bit longer. Escape velocity derivation. So kinetic energy equals gravitational potential. Half mv squared equals, and this one's gmm over r. We know that because potential or work done is equal to mass times by potential. Potential energy or work done is equal to mass times potential, and that's equal to mass times by gm over r. So I've just put it all together there. So let's get cancelling. Let's get cancelling one of our m's, and we should find that comes to v equals 2gm over r all square rooted. However, our question wants us to put little g in there. So gravitational field strength, how does that relate? Well, G is equal to capital G times by mass divided by R, and is R squared. So how does this relate to here? Well, they look kind of similar, so we might be able to use those. However, we've got R squared on the bottom and not here. So to get rid of that, I'm just going to put R on this side. So therefore, RG equals GM over R. So I can rewrite this as root, instead of GM over R, root RG or root GR. I've missed out the 2, which would be very bad if I did that in an exam. So therefore, it's going to be B, this one here. Okay, let's continue over here. This is a slightly tricky question. Talks about the period of rotation of a planet. Remains in contact with the surface of the planet. The speed rotates. It's very large. Now, what it's actually asking you, and it's kind of confuse you a little bit, is essentially to divide a relationship for t in terms of these things here. Now, you might be able to notice this looks kind of similar to Kepler's third law derivation. Okay, so let's just really quickly smash through that. Now we've got centripetal force is provided by gravity. So mv squared over r equals gm over r squared. So we're trying to find time period. So I'm going to cancel some m's first of all, and then cancel one of our r's. So v squared equals gm over r. To get t involved, I've got the speed is going to be equal to distance over time. It's the circumference, so it's 2 pi r over t all squared equals gm over r. Squaring everything out, it's going to be 4 pi squared r squared over t squared equals gm over r. This then becomes r to the 3. Get rid of this one. Rearranging this for t, so now I've got to rearrange nice quickly because I've not got much room, which is going to be 4 pi squared r cubed over gm. Now, which one looks like this? Well, if I square root the whole thing, square root of 4 is 2. I've got r cubed in there. I've got gm on the bottom. All these done is taking the pi out, so it's going to be c in this one. Last question. Satellites N and F have the same mass and move in circular orbits. Orbital radius of n is less than that of f, so r is lower. Which is smaller? So gravitational force on the satellite, nope, that's going to be bigger. Speed of the satellite, that's going to be bigger as well. We need to talk about the kinetic energy. Well, if the speed goes up, kinetic energy goes up. So it is the orbital period. So it's kind of asking you to use that relationship we just talked about, which is that if r goes down, t also goes down.